So we'll wrap up this Lecture 5 series here in this last chunk. As I've been alluding to in the first two parts of this lecture, we're essentially done discussing the basics of Michaelis-Menten enzyme kinetics and the variables Km, Vmax, and Kcat. We'll be moving on here to enzyme inhibition. What different molecules can we use to inhibit Michaelis-Menten enzymes, and specifically what effects can we predict will be had on the properties such as Km, Vmax, and Kcat. So enzymes are wonderful catalysts. I think we all can agree on that now. They make biochemical reactions occur at rates that would not otherwise make life possible. So enzymes are very much responsible for life being possible on this planet. But that's not always a good thing. Sometimes you can imagine a cell would prefer that a reaction not occur. Sometimes it's important for reactants to be left as reactants and for product not to be made. In other words, maybe we don't want to break down and release stored glucose immediately after a glucose-rich meal because we already have enough glucose coming in from our diet. It would make more sense there to keep those enzymes off so that we can store that stored glucose for later when we need it. In situations like this and in many, many others, the cell would certainly prefer to keep enzymes inhibited or turned off. And this is often achieved by using a molecule called an inhibitor. Also, enzymes behaving inappropriately. That is, they're doing their function, but they're doing it at the wrong time or in the wrong cellular place, can also be temporarily corrected by inhibition. In fact, many drugs that are developed by the pharmaceutical companies are enzyme inhibitors, and they work by turning enzymes off at particular times or in particular places, and that inhibition of the enzymes can restore a patient to full health. The text has a great write-up on HIV inhibitor therapies and how those inhibitors work to keep people harboring the HIV virus, keep their symptoms at bay. And so if you're looking for kind of a quick related read that's a little bit of interest, certainly check that out in the textbook. So in general, inhibitors can work to slow enzymes down in one of two ways. We have reversible inhibitors that are just that. Reversible inhibitors bind to an enzyme, inhibit its function for some amount of time, and then eventually those inhibitors let go, returning the enzyme to its original state, and the enzyme can then go off and bind to substrate if necessary. Enzymes that are inhibited in this way are unaffected long-term by the inhibition and can return to normal once they're let go by the inhibitor. Reversible inhibitors themselves also recycle because they are unmodified by this reaction as well, and so they can bind to other identical enzymes and repeat their inhibition. The second primary strategy is what's called irreversible inhibitors, and irreversible inhibitors do just that. They bind to enzymes irreversibly. Usually these inhibitors will bind to enzymes covalently, and so once those inhibitors are bound to an enzyme, the enzyme becomes permanently useless and can never return to normal. Likewise, the inhibitors themselves have sacrificed themselves because they are covalently linked to their target enzyme, and so sometimes irreversible inhibitors are also referred to as suicide inhibitors because they never recycle either, and they become permanently stuck to their target enzyme. Everything we talk about in this chunk is going to refer exclusively to reversible inhibitors. So once we've narrowed ourselves down to reversible inhibitors, there are three separate classes of reversible inhibitors that can influence Michaelis-Menten enzymes. Those classes are competitive, uncompetitive, and non-competitive. Don't get mad at me, I didn't name these. These are how these are named. I know that uncompetitive and non-competitive sound like the exact same thing, so we will have to use a little bit of memorization here, I think, to keep these separate. Competitive inhibitors, though, are the easiest to understand, so we'll start with those as our first example. These inhibitors have very, very similar molecular structures to the true substrate that the enzyme is meant to bind to. And so, because their structure, the competitive inhibitor structure, is so closely related to the substrate, these inhibitors bind directly to the active site. These inhibitors, in the real sense, compete with access to the active site with the true substrate, and that's the mechanism of their inhibition. When this inhibitor is around, it can bind temporarily to the active site, and that stops that enzyme from being active on true substrate. After a little while, the inhibitor will be let go of the active site, substrate can come in, and then the enzyme can get to work. So when the inhibitor wins this competition, and the enzyme is bound to the, when the inhibitor wins this competition, and the inhibitor binds to the enzyme's active site, true substrate can't get there, and catalysis will not occur. That's how we get our inhibition. Yeah, I want you to think for a moment, what shape or structure might an inhibitor have that makes it the most potent inhibitor imaginable? As I've been doing, I'm going to answer this question in just a second or two, but why don't you pause the lecture and think about this for a while. Try to dig back into your memory of what we've talked about before and see if you can devise a general shape or structure of an inhibitor that would be the best inhibitor, and by best we mean the most potent competitor for access to the enzyme's active site. The best, most potent inhibitors are those that resemble transition state. Remember, enzyme truly wants to bind transition state. That's what enzyme is always after. So if you can design an inhibitor molecule that mimics the overall shape and structure of transition state, enzyme will bind to that preferentially every time. Pharmaceutical companies figured that out quite a while ago, and some of the best drugs out there are small molecules that mimic the shape of transition states for the enzymes they inhibit. So let's go back to some of the common sense that we tried to grapple with in the last lecture series. Let's imagine in the case of a competitive inhibitor that the ratio of the competitive inhibitor to the ratio of true substrate is about 50-50. In other words, we have equal amounts of inhibitor present and true substrate present. You can imagine that there'd be a huge inhibitory effect here, because every enzyme at any one time has an equal chance of binding to substrate or inhibitor. Essentially, we'll cut the enzyme's productivity down in half. An enzyme would have a coin flip's chance of being inhibited in such a case. Now let's imagine we skew the scale so that the ratio is 75-25. In other words, 75% of the molecules out there are substrate, and 25% of the molecules out there are inhibitor. Enzymes in this environment would have a better chance at catalysis because the given chance that an enzyme has of binding an inhibitor is about 25%. What if we think about ratios of 99-1? What if 99 molecules out of 100 are substrate, and only one molecule out of 100 are inhibitor? Well, there we would barely see any inhibition at all, no? Because the amount of substrate is so high relative to inhibitor, we're going to see very little inhibition because most of the time, enzyme is going to be binding to substrate. And as soon as substrate wins that competition for the active site, it's as though the enzyme's not inhibited at all. So essentially what we see here in this mental exercise is that by increasing the amount of substrate more and more and more, you can diminish the effect of the inhibitor. The inhibitor can essentially be swamped out. Competitive inhibitors rely exclusively on having competition, being effective competitors for the active sites of enzymes. But if those competitive inhibitors just don't have the numbers, aren't there in a sheer enough force, it can't compete with a more numerous substrate concentration. This is the hallmark feature or trait of competitive inhibitors, that their effects can be swamped out by increasing amounts of substrate. Let's take this idea one step further. Let's imagine we have 99,999 molecules of substrate and 1 molecule of competitive inhibitor. 50 enzymes are present. Do you think those enzymes will be saturated with substrate? They most definitely would be. If those enzymes are saturated, is the reaction rate going to be Vmax? It most certainly would be. The enzymes would be at their maximal rate of productivity. So what we're really saying here is that the effects of a competitive inhibitor can be completely overcome as long as it's possible to add a sufficient amount of substrate. We can say that more succinctly by saying Vmax is unaffected by a competitive inhibitor. When an enzyme is in the presence of a competitive inhibitor, if you can add enough substrate, you can still achieve that Vmax maximal velocity. But Km is defined as the substrate concentration required to get to 1/2 Vmax. And if us achieving Vmax relies on us adding more and more substrate, that means we have to add more and more substrate to get to 1/2 Vmax as well. So in the presence of the inhibitor, we can get to Vmax, but it takes a whole lot more substrate to get there. And likewise, in the presence of a competitive inhibitor, we can still get to 1/2 Vmax, but we need more substrate to get there as well. So in the presence of a competitive inhibitor, Km goes up so that we can achieve that saturation. We need more substrate to get to saturation. And Km going up, remember, looks like a poorer binder. In the presence of a competitive inhibitor, it appears as though the enzyme binds to substrate more poorly. And yes, it does, because it's competing with inhibitor to get there. So let's look at this schematically, graphically, rather than saying it with words, and this will hopefully lock this idea into place. And what we see here is a reaction. In green is the reaction without an inhibitor. We're back to a Michaelis-Menten graph here, not a Lineweaver-Burk. And we see what we're kind of used to. We have substrate concentration on the x-axis, the rate of the reaction or the velocity on the y. Here is Vmax, the maximal rate of the reaction. And we have our 1/2 Vmax is probably about here, I'd say. We draw a line to the curve, drop down, and so this is our Km, more or less, right here. In the presence of the competitive inhibitor, we can still achieve Vmax. See, we can still get to that maximal velocity. But it takes more substrate to get there. Here, we reach the Vmax at around this substrate concentration, more or less. Here, we have to go all the way up to this substrate concentration in order to achieve the same Vmax. So we get to Vmax, but we need more substrate to get there. If we say that this is Vmax in both cases, and we say that this is about 1/2 Vmax in both cases, our Km without inhibitor was here, but now our Km with inhibitor is here. That's a higher Km value now, indicating poorer binding because we have to deal with the effects of the competitive inhibitor. So here I indicate the Km without inhibition, and this is the Km with inhibition, and we can see that Km value goes up. On a Lineweaver-Burk plot, it looks a little bit different. The blue curve here shows us a lack of inhibition, and we can see in the presence of no inhibitor, we have some value for Vmax, again this is the reciprocal of Vmax, and we have some value for Km. When we add some inhibitor, we see that our y-intercept is unchanged, because Vmax is unchanged. 1 over Vmax is not changed, and so that line still intercepts the y-axis here. But we also see that Km has changed. In this case, the reciprocal of the Km value has gone down in value, which means Km itself has gone up. If we add even more inhibitor, twice as much inhibitor, we see that still Vmax is unchanged, but Km has gone up even more. So increasing amounts of inhibitor lead to higher and higher values of Km. In other words, the enzyme is binding to substrate more and more poorly. So the hallmark features of competitive inhibition is that Vmax remains unchanged because we can still reach our maximal velocity. Km goes up because we have poorer binding. We need more substrate to reach Vmax. And whatever Vmax does, Kcat does. They travel together. So since Vmax was unchanged, our turnover number is unchanged as well. Once we get to the enzyme substrate complex, we can create product from there. On now to uncompetitive inhibitors. Uncompetitive inhibitors are not all that thoroughly explained in the text, but they're quite important. We can learn a good amount from them about Michaelis-Menten kinetics in general, so we'll cover them here a little bit more robustly. Uncompetitive inhibitors bind to, and only bind to, the enzyme substrate complex itself, and they stop the enzyme substrate complex from progressing to product. So here we see that the inhibitor can only bind to the ES complex. It almost bear hugs the ES complex. The inhibitor cannot bind to enzyme alone. It cannot bind to substrate. It can only bind to enzyme substrate complex. This class of inhibitor requires the substrate to bind to the enzyme first, and only then can it exert its inhibitory effect. Once inhibitor binds to the enzyme substrate complex, that enzyme is out of the game, at least temporarily, and we cannot proceed towards product. Therefore, since this enzyme is out of the game and unrecyclable, there is no amount of substrate possible we can add that can outcompete this inhibitor, because there's no competition for substrate binding in the first place. In fact, substrate binding to enzyme feeds the inhibitor, and so adding more substrate cannot help us get out of this inhibition rut. Therefore, in the presence of an uncompetitive inhibitor, Vmax is functionally lower. We cannot achieve the same maximal velocity in the presence of an uncompetitive inhibitor that we can achieve in its absence. The maximal rate of the reaction is lower, period, because the inhibitor results in fewer functional enzymes being present. Interestingly, Km also goes down in the presence of an uncompetitive inhibitor. Now think about that for a second. That makes no sense. A lower Km value means what? A lower Km value means better substrate binding. Why in the world would an inhibitor binding to an enzyme substrate complex make it appear as though the enzyme were binding to the substrate better? Well, the reason is because the inhibitor, by binding to the enzyme-substrate complex, actually stabilizes that complex. Remember when I showed you E plus S going to the enzyme-substrate complex, and we talked about K minus 1, the reverse reaction. Every once in a while, enzyme-substrate complex can fall apart back to enzyme and substrate. That doesn't happen in the presence of an uncompetitive inhibitor. The uncompetitive inhibitor stabilizes enzyme-substrate binding. That's its mechanism of inhibition. That stabilizing of the enzyme-substrate complex stops transition state from forming. And since the enzyme-substrate complex is now so happy together in the presence of inhibitor, and transition state will never form because of that thermodynamic happiness, product is never made. There's your inhibition. So if we look at Michaelis-Menten graphs in the presence of uncompetitive inhibitor, we can see that when there's no inhibitor present, we have a fairly typical Michaelis-Menten curve here. Vmax would be up here. If we add some inhibitor, we see that that Vmax decreases. That Vmax goes down. Add more inhibitor, it decreases even more. Add more inhibitor still, it decreases even further. If we look at a Lineweaver-Burke plot, we can tease out some of these factors a little bit more as well. As we increase the amount of inhibitor, we're going from the uninhibited line in blue to increasing amounts of inhibitor in red. We see that the y-intercept is getting higher and higher in value with increasing amount of inhibitor. Remember, this is 1 over Vmax. So 1 over Vmax getting higher and higher means that Vmax itself is getting lower and lower. With increasing amounts of inhibitor, Vmax goes down. We also see with increasing amounts of inhibitor that the value of 1 over Km, the reciprocal of Km, is getting bigger and bigger and bigger. If 1 over Km is getting bigger with increasing amounts of inhibitor, that means Km itself is getting smaller with increasing amounts of inhibitor. In other words, it appears as though the enzyme is binding to substrate more stably, more tightly, and indeed it is, because the inhibitor is stabilizing that binding. So the hallmark features of an uncompetitive inhibitor is that Vmax goes down with increasing amounts of inhibitor. We can't reach our uninhibited maximal velocity. And Km goes down as well, because the inhibitor is stabilizing the enzyme-substrate complex. That enzyme looks like a better binder. Whatever Vmax does, Kcat does as well. So Kcat is going down because it's directly related to Vmax. The functional turnover number of the reaction is indeed slower. Remember, this inhibitor works by taking away functional enzymes. So that's its enzymatic mechanism, its inhibitory mechanism. Non-competitive inhibitor, our last class, is probably the most confusing, so we won't go too much into the detail of it, but it's important to say that non-competitive inhibitors kind of branches us into the realm of allosteric enzymes. This is where the boundary between Michaelis-Menten kinetics and non-Michaelis-Menten kinetics gets a little gray and fuzzy. Michaelis-Menten enzyme kinetics is exclusively for non-allosteric enzymes. Non-competitive inhibitors have an allosteric effect. So we are transitioning now away from Michaelis-Menten thinking and towards allosteric enzymes, and we'll stay there for a little while in the upcoming lectures. Here, the inhibitor binds to some second binding site elsewhere on the enzyme. Therefore, the inhibitor can bind to the enzyme whether the enzyme is on its own or the enzyme has bound to substrate. So here's the inhibitor as this yellow oval circle, and we see that that inhibitor has its own binding site elsewhere on the enzyme. The active site is here in this boxy form, bound by the substrate, which is this orange rectangle. So inhibitor can bind to the enzyme when substrate is absent. Inhibitor can bind to the enzyme when substrate is present. And again, it can do this because the inhibitor has its own distinct binding site, far from and separate from the active site. This can also be referred to as an allosteric site, because when the inhibitor binds here, it changes the shape of the enzyme. Therefore, non-competitive inhibitors do not affect substrate binding at all, because the binding of non-competitive inhibitors is completely independent of the active site. If that's the case, which value do you think will never change, even in the presence of non-competitive inhibitors? If you said Km, you did great. Km deals with substrate binding. And so if substrate binding is not changed, neither will be Km. But non-competitive inhibitors inhibit. They slow the reaction down. They impede catalysis. So which value do you think will change as a result of the presence of a non-competitive inhibitor? And hopefully you said Vmax. You might have said Kcat as well. Both answers are correct. Vmax and Kcat change in the presence of a non-competitive inhibitor. And which way do you think they change? Do you think those values go up or down? And they do go down. The rate of the reaction and the velocity of the reaction decreases in the presence of inhibition. So here's a nice Michaelis-Menten plot of the effects of a non-competitive inhibitor. Here in green we have the absence of the inhibitor. Again, we have some Vmax up here, and we have some Km over here. In the presence of the inhibitor in red here, we see that the enzyme slows down, and we can never achieve the same Vmax. But if we calculate and estimate the Km, if this is Vmax, this is about 1/2 Vmax, we draw a line to the curve, drop that line down, we see that Km has not changed at all. Hallmark feature of a non-competitive inhibitor. We can see the same effects on a Lineweaver-Burke plot. Here is the presence of the enzyme, of the reaction in the absence of the inhibitor. We have 1/Vmax as our y-intercept and 1/Km as our x-intercept. As we add inhibitor, we see the slope of the line changes. Now our 1/Vmax is a higher number, indicating that Vmax itself has gone down, but our x-intercept is exactly the same. The Km value has not changed, so neither too has the x-intercept. Vmax goes down, we can't reach our uninhibited maximal velocity in the presence of a non-competitive inhibitor, but since this inhibitor is binding completely independent of the active site, we don't affect substrate binding at all, and say Km remains unchanged. As we've been saying all along, whatever Vmax does, Kcat does as well, and so Kcat goes down as well. As we increase the amount of substrate, we can't affect Vmax because substrate binding has nothing to do with the inhibitory mechanism. There's no way we can swamp out the effects of the inhibitor with increasing amounts of substrate. So one good way to summarize all this material is actually to test ourselves. Here we have 3 schematics. On the top, we see the mechanism of inhibition. In each case, the inhibitor is present as a blue diagram, and the substrate is present as a red triangle. And on the bottom, we see the Lineweaver-Burke plots representing each of these. And so we have to ask ourselves, which of these represents a competitive inhibitor? As we go through these questions, I'll answer them soon after I pose them. But again, I encourage you to pause the lecture and think it through. This is the type of material you'll have to be able to master for the exam. So competitive inhibition. Well, let's refresh ourselves. Competitive inhibitor. We can swamp out the effects of a competitive inhibitor as long as we have enough substrate. As long as we can swamp out the effects, that means we can eventually get to Vmax. So for competitive inhibitors, Vmax is unchanged. Vmax is the y-intercept. Only this graph here shows the y-intercept being unchanged, and so this represents a competitive inhibitor. Let's look at our schematic to see if it's true. This schematic shows the inhibitor binding to the active site, or the substrate binding to the active site. The inhibitor and the substrate are competing for access to the same region. Of course, that is a competitive inhibitor. Which represents an uncompetitive inhibitor. For uncompetitive inhibitors, we do something a bit different. We bind to the enzyme substrate complex, which means we lower Vmax because we can never achieve our maximal velocity, but we lower Km as well because the enzyme substrate complex is what the inhibitor binds to. The inhibitor solidifies or stabilizes that enzyme substrate complex. So let's look for a Lineweaver-Burke plot where we have a decreasing Vmax and a decreasing Km, and that looks like it's this one here. As the amount of inhibitor goes up, so too does the value of 1/Vmax. That means Vmax is going down. So too does the value of 1/Km. That means Km is going down. This looks like an uncompetitive inhibitor to me. And if we look at the schematic, we see the inhibitor in blue is only binding to the enzyme substrate complex and nothing more. Definitely our uncompetitive inhibitor. That means process of elimination tells us that B is the non-competitive inhibitor, but let's be sure of that. Non-competitive inhibitors bind to their enzymes whether they're substrate bound or not. They have their own secondary binding site. And since there's no influence on substrate binding whatsoever, Km remains unaffected. Only Vmax goes down. And here we see in this Lineweaver-Burke plot, it's the x-intercept that is unchanged, and that's because the 1/Km value never changes in the presence of inhibitor, because Km isn't changing. Substrate binding is unaffected. What is changing is Vmax. With increasing amounts of inhibitor, 1 over Vmax goes up, which means Vmax is going down. If we look at the schematic, we indeed see this separate binding site exclusively for the inhibitor, and the inhibitor can bind to that site whether substrate is bound or not. So B is definitely our non-competitive inhibitor. We're going to be moving on to how we regulate enzymes next. That's going to take us into the realm of allosteric enzymes. So we begin discussing non-Michaelis-Menten enzymes in Lecture 6 and the chunks that come with it. Please definitely make sure that you're comfortable with these concepts. If not, come see me right away. Let me know in your reflections, and we'll get you squared away. I've said it before, and I'll emphasize it now. We build and build and build in this course, and so we want to make sure that each time we end the lecture, that foundation is solid, because we need to build on those concepts as we move forward in the course. As always, thank you so much for watching. I'll see you in the next lecture.